installment of our grand physics journey. By this point, you should be somewhat comfortable, at least, with our equations of motion as they pertain to one dimension, just moving straight up and down a track, jumping straight up in the air, or running horizontally. But if you're like me, that gets pretty boring pretty quickly. I don't want to just jump straight up. I want to launch myself in some direction, figure out where I'm going to land and when I'm going to land there. So that brings us to motion in 2 dimensions. So, if you've got an object that's not just moving up or down or left or right, that's when you can break it into x and y components, and it's why we spent so long at the start of the year breaking down vectors into x and y components. On this image on the screen, you see a velocity vector pointing up and to the right. That means something has some velocity up and to the right. So I can break that down into its x component of velocity, how fast to the right is it moving, and its y component of velocity, how fast up is it moving. Once I do that, the exact same equations of motion work, but they also have to only deal with one component at a time. Remember earlier I talked about how you cannot add things with different units. No raccoons plus cupcakes, no cupcakes. Same deal, except now, not only can I not add things with different units, I cannot add things together if they're in different dimensions. If they're in different directions, how about that? So what happens in the y direction, which is vertical, does not in any way affect what happens in the horizontal x direction, and vice versa. They both operate independently. So once I break that vector down, I can head to my equations of motion, but now I've got more to deal with. All the equations are exactly the same, the position equation, the velocity equation, the combo equation, but I've added little subscript x's and little subscript y's to explain what's going on. So, for the position equation, it's not just d equals d naught plus v naught t plus 1/2 at squared. If I've got 2 directions happening at once, I've got my horizontal position equation. This tells me how far I've moved to the left or right over any course of motion. And that's little d subscript x equals d naught x plus v naught x times time plus 1/2 ax t squared. Same deal on the other side. If I'm looking at my vertical motion, I've got d with a subscript y equals d naught y plus v naught y times time plus 1/2 ay t squared. And so on and so forth for all of the equations. So all I've done is for every single vector, velocity, position, acceleration, added a little subscript x or y, depending on what direction I'm heading in. We did earlier a special case of free fall. In free fall, you automatically know what your acceleration is, and that hasn't changed now that we're in 2 dimensions. The only difference is gravity only accelerates objects vertically, specifically vertically down, which means if I am in free fall, again, no force acting on me except for gravity. I'm not touching anything else, essentially. I'm just falling, even if I'm moving to the right or left while I do it. This picture shows a kid jumping off of a rock into some water, traveling forward, rightwards, horizontally, while also accelerating downward. So that tells me that for the entire motion, my velocity in the x direction will be my initial velocity in the x direction. Now again, that's only free fall. If I am sprinting, let's say, I can still accelerate in the x direction. So again, only in free fall will I have no acceleration in the horizontal direction. And the reason that vx equals v naught x for the entire motion is just the velocity equation. Vx equals v naught x plus ax t. Well, with only gravity acting on me, my acceleration in the x direction is 0, leaving only vx equals v naught x. That's kind of nice. This is a little chart of projectile motion. Basically, if I have some velocity initial velocity up and to the right at some angle theta above the ground or above the horizontal, I can break that down into its x and y components, just like any other vector. Now, once it starts moving upward, there's a constant downward acceleration of gravity of 9.81 meters per second squared. So as it moves up, the y component of velocity gets smaller and smaller until it reaches 0 at the top. Now that we're doing it in 2 dimensions, the x velocity does not necessarily reach 0 at the top. I can keep moving rightward, but the y velocity reaches 0. And then, due to gravity, bit by bit, it accelerates downward, and the y velocity gets bigger and bigger. Meanwhile, through this whole motion, the rightward velocity is exactly the same as what it began with. There's no acceleration in that direction. So, if you find you have a little bit of extra time, I've got an optional video posted that's just me working through an example of 2-dimensional projectile motion. So take a gander at that if you've got a bit of extra time. Otherwise, I will see you in class. Take care.